Okay. Picking up in Chapter 2 for Lecture 2. Okay. So in Lecture 1 of Chapter 2, we talked about what it meant to actually apply a force and do work. And remember, for the two things, you have to apply a force, and then the boundary must move. So you need both of those for work to exist. Now we get into different types of work, and there's many, many different types. One is shaft work. And so here's the formula for shaft work, but then here you have a little schematic. Shaft work is proportional to the torque applied and the number of revolutions on the shaft. So, of course, you're probably thinking of a wheel or a tire or, a rim, something like that. But this is the shaft work. So you have the torque that is applied and then the revolutions that it produces. Okay? And then energy transmission through rotating shafts is commonly encountered in practice, of course. So you see lots of modes of transportation uses it, but to propel different things, right? So we have an engine over here, it's applying torque, and then you've got revolutions over here on the turbine, on the fan. Then you have spring work, which is, here's the formula here, but elongation of a spring under the influence of a force, right? So you can, we have a rest position right here. Come over here, we have a rest position. Oops. I have a pen that I use for these, and there's buttons on the side of the pen, so I'm always hitting them. So here's the rest position, and when you apply some compression, you will be loading up the force and the spring will get smaller, or you can do tensile and you can pull the force, right? So when the length of the spring changes by a differential amount to dx under the influence of a force, whether it be compression or tension, the work is done. And so you see it gives a formula there, and then it gives work for spring formula as well. And then you see down here where it says x1 and x2, those are the initial right here and the final displacements. And then it just has it over here where it's actually where you're seeing this displacement. So this is the initial and this is the displacement, and kind of how that works as well. And you see you've got the rest position. Okay. And it's when the force is doubled. So really, if you wanted to take it from the rest position, this would be F1, this would be F2, and this would be F3, right? But it depends. You may be looking at just the initial loads. Okay, and so work done on elastic solid bars. So it has solid bars behave as springs under the influence of a force. I want you to think of this as, I know this might be hard to picture, but alloys, metals, polymers, plastics, things like that, you can stretch them, right? They will stretch. They won't just break in half. You can stretch wood. It takes an incredible amount of force and the right tools to do it so that it doesn't shear and break. However, we played with these when we were a kid, but like the little stretch, toys or whatever. Or if you get on a board and it starts to bow, even though that's not complete stretch like a spring, you can see that material deforming. So you definitely can have a force applied on a solid and it move. And this is an instant when you have elastic means that it can deform and go back. So just like a rubber band, if you stretch it out, it's very elastic and it'll come right back to it, right? So this could be like F1 and F2, right, of a rubber band. You can also do that for solids. And if it goes back, it would be reversible. But if it didn't go back, say your rubber band was right here, and you stretched it out, and then at the end, it came to here. So it never went right back to here. This is irreversible. So it never went back to the very beginning. Work associated with stretching of a liquid film. So these are, just exactly what it says, a liquid film. Stretching a liquid film with a U-shaped wire when the force is acting on a movable wire length. So this is just showing how, if it's rigid wire frame, surface of the film. So you can think of this like glass maybe, or maybe like cling wrap, some kind of film. I'm trying to think of like an everyday example, but it's attached to these sides, and then you would move this and it would stretch it. Okay. And then work done by raise or accelerate of a body. And so you see here the elevator car. Where's my pointer? Oh, it's gone. There it is. Okay. All right. So you see here you have a motor and it's just spinning. And here you've got some shaft work going on, right? Of course. You got some shaft work going on, and so we've got some revolutions here that's pulling up the cable, if that's, the way that this is going. And so then this would be to raise this cable car, or if it's spinning the other way, right, then it would be going down, just depending on which way the motor is turning the shaft. The work transfer needed to raise the body is equal to the change in the potential energy of the body. The work transfer needed to accelerate a body is equal to the change in the kinetic energy of a body. That makes sense. It's just saying that, I know that that's very wordy, but it's just letting you know that potential energy and kinetic energy is dependent on if you're accelerating a body or if you're raising a body. So if you're raising or if you're accelerating, right? Okay. So now we have non-mechanical forms of work, so which is electrical work, magnetic work, and electrical polarization work. We won't be delving in too much into these, but it is important to know, and it's also important to know if you plan on doing electrical engineering or things like that, that these are the industries that you will delve into, right? So the generalized force is the voltage in electrical work, right? And we kind of went into that. We used an example of the refrigerator in the room, and we had some association through the boundary with the surroundings, and that was done by voltage. You've got magnetic work. And so it's a force, it's generalized a magnetic field strength. Strength with the generalized displacement is the total magnetic dipole moment. So that's when you start getting into a lot of medical industries use these magnets and things like that, like an MRI machine. And then electrical polarization work, the generalized force is the electric field strength, and the generalized displacement is the polarization of a medium. And you have a compass. So that's how that's done. It's done with the polarization of our Earth. So we're going to get into the first law of thermodynamics. And we did talk about this in the beginning. And remember, the first law of thermodynamics is also known as the conservation of energy principle. It provides a sound basis for studying the relationships among the various forms of energy and energy interactions. The first law states, this is extremely important. The first law states that energy can neither be created nor destroyed. We cannot create energy. We cannot destroy it. We can only change forms. It says it cannot be created or destroyed during a process. As we are concerned, it cannot be created or destroyed. All of our energy comes from the sun. We cannot create the sun. So I want you to think of it as that, and you can't destroy the sun. So just think of that. We are only transferring it. We are only changing forms. Just like this example on the right where it's changing from potential energy to kinetic energy, but we still have 10. We still only have 10. We don't have any more energy. We don't have any less energy. We didn't create anything. We just changed the energy. That's it. And we do that using windmills, turbines, when we are extrapolating energy out of fossil fuels to make fuel to then use for shaft work in our car. It's going through so many different types of processes. For adiabatic processes, this is the first law. For all adiabatic processes, what is adiabatic? Remember, what does that mean? Adiabatic means, Q is equal to 0. There's no heat transfer. For all adiabatic processes between two specified states of a closed system, the net work done is the same regardless of the nature of the closed system and the details of the process. Okay? And then energy cannot be created or destroyed. It only changes forms. It's listed twice on here for a reason. You need to know this. You need to know, all of this, right? That's why I'm teaching it. But this you really need to understand. Anything you do in this class and thermodynamics right here, thermodynamics is natural laws. First law, second law, 0th law. Remember that did the temperature, basically made us able to measure it. All of those are natural laws. So you're not going to go out in the world and create energy. You may transfer it. Fission didn't create energy, but it definitely found a new way to transfer it, to convert it, to change it. But no one's creating more energy. No one's destroying energy. Then that kind of gets into efficiency, right? So are we able to get 100% of the energy that the sun puts out to Earth? Well, of course not. We get negligible amounts. We get hardly anything compared to what is put out. And that's because it's not efficient. A lot of it's lost in space. A lot of it is lost. It goes on every blade of grass when you're standing outside. It goes on the fence. It goes on a tree. It goes on, everything. And so you're not able to capture everything. So just like when you are talking about a water mill that is converting energy into usable energy, it's also not going to be 100% efficient, right? We're going to lose some of it to friction. We're going to lose some of it to the atmosphere. We're going to lose some of it to the actual equipment. We're not going to be efficient in capturing it all, but it is all there. We didn't destroy energy. We just weren't able to capture it all. Okay, so here you have QN, which is heat transfer in. To increase the energy of a potato in an oven the increase in energy of a potato in an oven is equal to the amount of heat transferred in. So this delta right here means change. The change in energy is equal to 5 kilograms. And that's the heat transfer in that we've gotten in. Okay. And then here we have, in the absence of any work interactions, the energy change of a system is equal to the net heat transfer, right? Because how do we transfer energy? Heat or work. So if we don't have any heat, we're going to have work. But, if we're looking at a system, unless there's nothing being done on it and it's isolated, right? But if you're looking at something and the change in energy, if it doesn't have one, it'll have the other, if that's what we're looking at, right? The work electrical done on an adiabatic system is equal to the increase in the energy of the system, right? So we're not getting any heat transfer through the boundary. So the work, which is electrical, which goes through here in an adiabatic system, is equal to the increase in the energy of the system in the system that comes in, right? The work shaft, so right here you see the revolutions on it, right here. Okay. The shaft work done on an adiabatic system is equal to the increase in the energy of the system. See? So they have these shoots. See, work shaft, and it's in because shaft work is going in. You could draw this and have the shaft work going out, right? If you had a setup here. So make sure that you are denoting also whether it's in or out so that you know if you're gaining or losing. The work or the boundary work, see right here, you've got denote boundary work and it's going into the system, done on an adiabatic system is equal to the increase of energy of the system. So these are just giving you some parameters to understand when you're talking about adiabatic. And also something that's really important here, because you don't see any heat transferring through the boundary. Something that's really important here is that you are able and being able to see and define how things relate with the boundary and with the system, and also the assumptions that we have to make, right? We're not taking into account the friction that's happening right here. We're not calculating that, right? We're not calculating the friction that's happening from this piston going up and down. We do assume it is frictionless. Unless it's otherwise stated, it's always going to assume frictionless. And if you remember when we talked about tips on how to solve, you have your assumptions that you'll need to write down. This is a good one. So here's the energy balance. So total energy of the system entering the system, energy in, less the energy leaving the system, energy out, is the change in the system energy, right? Makes complete sense. If we have energy in, which is 100, or too many. All right. So if we started at 0, if our system started at 0 and energy in was at 100, and then we had energy out at 50, and we started at 0, well, how much would we have? First, we had energy in, so our system went to 100. And then we had energy out, so we're going to less the 50. And then we have 50. That's it. So the change in the system was 50. We started at 0, and we ended up at 50 because we had 100 come in, and then we had 50 leave. The net change, increase or decrease in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during the process. So that's a very wordy way of just saying it's the difference. Okay, and so here's an additional formula. So you've got energy change equals energy at the final state less the energy at the initial state. We just talked about that, right? So what is the initial change? What's the energy at the final state? 50. What is the the previous example? 50, right? That's our final state right here. 50. And then what was our energy at the initial state? 0. So 50 minus 0 is the energy change, right? And so you've got some formulas here. And then you've got the change in KE equals the change in PE equals 0. Thus, the change in energy equals the change in U. So here's some formulas. This one right here is really good. And you can just move it around. That's what it's showing you, that you can just move things around. But here, the change in energy equals the change in U plus the change in kinetic energy plus the change in potential energy. And remember, use internal energy, because the total sum of energy equals U plus KE plus PE, those three. So if we're looking at the change in E, it's going to be all of those added up, but they're changes. The change in U, the change in KE, the change in PE. And so then you can, just kind of start moving them around. And then here we have, incredibly important, you will need these. You have the formulas for each one of them. So what is the change in U? It's the mass times multiplied by U2 minus U1. So the internal energy at state 2 less the internal energy at state 1. So see, we are concerned about what happens in between. What if at our state 1 it was 100, And at state 2, it was 50. And what if our mass is 2? Those numbers don't make sense in the real world, but they do for this, simple thing. Right here, our internal energy is going to be 2 times 50, which is going to be 100. That's going to be our internal energy. We're not concerned about what actually is at U2 or at U1 from a interpretation point. We only need it to get what we need, which is during the process. These are during the processes, right? And so you have the same for kinetic energy and the same for potential energy. And remember, this is the gravitational constant. I believe it's 9.08 or 8.09. I'll have to find that out. You know what? Let me just erase that because I always get it backwards. But this is the gravity constant. I don't want to tell you wrong. Okay. And these numbers, if you're wondering like, oh my gosh, where are we going to get V and Z and U and things like that? We have a ton of tables, and that's where we get that data from. So here's just more additional formulas that we'll be using, and it's the mechanisms of energy transfer, E in and E out. You're going to get a lot of practice with that. Okay, and so then we have it at a rate form. Again, I don't know what is going on with these, but it's okay because we have formula sheets that we'll be using. You're not going to be referring back to these to pick up your formula anyway. And then down at the bottom for constant rates, the total quantities during a time interval, which is the change in T, are related to the quantities per unit time. And then we have these. Q is equal to Q delta T. So it's just saying, hey, it's relative to the actual change in time as well. And then we have the energy mass balance can be expressed as a per unit mass basis, of course. And then we would just take into account the unit mass for that. And so what you do is you obtain that divided by all quantities by the mass, right? So we're just taking it into account. And we do have differential form down below. And then we have mechanisms of energy transfer. Remember, we have heat transfer, work, and mass flow. So I have been harping on that the way that you can transfer energy is through heat transfer, which is Q, and then through work, which is work. We add on another one for calculation purposes, and it's mass flow. So when you're talking about when you have just a mass flowing and you have mass flow rates and things like that, that is actually work being done. It's just so large of a section that we do exclude that out for calculation purposes. But the two ways energy transfers is through heat transfer and work, right? But for calculation purposes, you will have an additional for mass flow. And so then here you see mass in and mass out, right? So if you really want to get into it, say this is water, right? And it's going in here, it's going into this control volume. There's heat transfer, there's work being done. Maybe there's a fan. It doesn't matter what it is. But there's water going in here. And then there's water going out here. Okay? And so you have heat being done, you have work being done, but this mass is also completing its own work. And so that's when we can start getting into the energy right here. The energy content of a control volume can be changed by mass flow as well as by heat and work interactions. So it can change the energy, but it's not so much a vessel of it that's different from work or heat transfer. We're just including it, again, purely for simplicity of calculating. We talked about this. Efficiency is one of the most frequently used terms in thermodynamics, and it indicates how well an energy conversion or transfer process is accomplished. I joke because when I see this, I think Is it one of the most frequently used terms because it's saying that it can never be completely efficient? Or is it because we're measuring efficiency? Because I think that they're both quite a lot. So one of the projects that I usually do is to measure the efficiency of your air conditioner. And you think, maybe when you hear that, you think, oh my gosh, that seems like an ordeal, like a big project. But really, you're just measuring the desired output and then the required input. And so it's really just two individual temperature readings that you can plug in there. And so here, the ratio of the energy delivered to a house by a hot water heater to the energy supplied by the hot water heater. And if you look down here, you have gas, conventional high efficiency, electrical, and electric high efficiency. And if you have just a conventional gas, your efficiency is only 55%. It is not very efficient, right? And now that we've gotten, electricity's gotten more efficiency and you have high efficiency on top of that, you can get up to the 94 range. But that's quite the difference when you're talking about how efficient your hot water heater is to your home. So heating value of the fuel, so the amount of heat released when a unit amount of fuel at room temperature is completely burned, and the combustion products are cooled to the room temperature. Lower heating value, LHV, was when the water in the combustion gases is a vapor. And then on the other side, high heating value, it's when the water in a combustion gases is completely condensed, and thus the heat is vaporized and is also recovered. So we can also go into those different forms of efficiency and what we're able to recover from those. The definition of heating value of gasoline. So we're just going into, and you can see that we are able to, the lower heating value, we're able to compute that. And you can see that combustion chamber inlet for gasoline and air, and then what comes out as well. And then the efficiency of the space heating systems of a residential and commercial buildings is usually expressed in terms of annual fuel utilization efficiency, which accounts for the combustion equipment efficiency as well as other losses such as heat loss to unheated areas, startup and cool down losses. So this is just going to kind of take into account everything that is reasonably expected to take into account, right? So if you're heating an entire building, you do want to know what's lost to just unheated areas, because remember, heat flows from hot to cold. So if you have a hot room or a heated room right next to a storage room that you're not heating, heating's going to flow and you're going to be, in essence, indirectly heating that cold room. And so that'll be a loss because you don't actually need that room to be heated. So the AFUE is the most new heating systems, and you've got about 85%. However, old heating systems is under 60%. So it's quite the difference. And you can start using these numbers to see if it's worth it to do certain things like replacements, right? And then some new heating efficiency furnaces exceed 96%, which is pretty amazing. But the high cost of such furnaces cannot be justified for locations with mild or moderate winters. So when you go out and you think, oh my gosh, this thing is the best, it's going to be 98% efficient. This is fantastic. It is $50,000 and you're wearing shorts on Christmas. It's probably not the best choice for you. But if you're in Alaska where you are heating a residential complex, this may be a good idea for you because it's very cold. Or, if you're in Finland or any of those in the Arctic Circle, or at the labs in Antarctica, some of these things, something like this that is very costly may be worth it just to get that efficiency, especially in places where maybe it's really difficult to get the working fluid. It's very difficult to get the fuel. Such high efficiencies are achieved by reclaiming most of the heat in the flue gases, condensing the water vapor, and discharging the flue gases at temperatures as low as 38 degrees Celsius or 100 Fahrenheit instead of about 200 degrees Celsius or 400 degrees Fahrenheit for the conventional models. What is happening? So here is for the overall efficiency of a power plant. So you see you have some formulas over here, and then you just multiply the efficiency of the combined equipment, thermal, and then generator, and that equals the network electric over HHV times mass over fuel. Again, I don't know what these are. I'm going to have to go in and see why they don't look like that until I start presenting them. And then here are some devices that you'll need to know. A generator is a device that converts mechanical energy to electrical energy. The generator efficiency is the ratio of the electrical power output to the mechanical power input. And then thermal efficiency of a power plant is the ratio of the net shaft work output of the turbine to the heat input of the working fluids. So those are just some definitions for you to know what is what, but the overall efficiencies are about 25 to 35% for gasoline automobile engines. I mean, low, right? 35 to 40% for diesel engines, a little bit better, and then up to 60% for large power plants. So when we're talking about converting energy, and when I talked about, we don't get all of the energy from the sun, it's because we're not able to harness all of it. So even here, we're only able to harness 60% of what we're actually converting. That's all we have. Or when you put in gas for your just regular gasoline automobile, then your efficiency is only about 25 to 30%. They're actually very inefficient, but when you look over at total efficiency, you're never getting 100%, and you're often, very often, the majority of the time, not getting anywhere close to that. So sometimes when a new product is released and it's at 50% efficiency, they are cheering because it's the highest that they've ever gotten. And so here we've got the efficacy of different lighting systems. So lighting efficacy is the amount of light outputs in lumens per watt of energy consumed. And so just a little note, this value depends on the spectral distribution of the assumed ideal light source. For white light sources, the upper limit is about 300 lumens per watt. For metal halide, 350 lumens per watt. For fluorescence, 400 lumens per watt. LEDs. Spectral maximum occurs at a wavelength of 555, which is green, and then a light output of 683 lumens per watt. So over here, you've just got the efficacy of different types of, LEDs. You've got mercury vapor, you've got compact or tube, ordinary, halogen, candle. Not a lot, right? Okay, and so a 15-watt compact fluorescent lamp provides as much light as a 60-watt incandescent lamp. So that kind of helps you understand, if you are talking about a fluorescent, you only need 15 watts to produce the same as an incandescent at 60. Right, that's a fourth less. Okay, and then here's some more about efficiency just with different units. So efficiency over here is equal to energy utilized over energy supplied to an appliance, right? And then using energy efficient appliances conserve energy, of course, because it's energy efficient. Helps the environment by reducing the amount of pollutants emitted to the atmosphere during the combustion of the fuel. So maybe not exactly when you are using it, but from the production standpoint to produce those things, it definitely helps with that by reducing the pollutants. But also maybe in the combustion if that's where you're using or where you are the user of it. The combustion of fuel produces carbon dioxide, Nitrogen, carbon monoxide, and sulfur dioxide. My favorite because it causes acid rain. It's just fantastic. So, maybe get an energy efficient appliance. It helps. The efficiency of a cooking appliance represents the fraction of the energy supplied to the appliance that is transferred to the food. So it's just that fraction. And then here's some cost as well, like what it costs to actually use these appliances. For an electric oven, which is 19 cents, frying pan, which is 9 cents, toaster oven, which is 9 cents, crock pot is 7 cents. I had no idea. And a microwave is 3 cents, I'm sure, because look at the time differences, right? Huge differences. But let's look here. So gas oven and electric oven, gas is significantly less for the same hour and the same temperature. So that would be a good one to compare, right? And then here, it's great. It is 7 cents. It's way cheaper, but you have to cook it for a lot longer, right? For that 7 hours. Okay. Oh, you know what? This is a good thing. Look down here. They even put their assumptions. Okay. And then the efficiencies of mechanical and electrical devices. So here's the mechanical efficiency. It's just output over input. And then the effectiveness of the conversion process between the mechanical work supplied or extracted and the mechanical energy of the fluid is expressed by pump efficiency or turbine efficiency, just whichever is applicable there. So you have the pump, which is the energy increase of the fluid over the energy input. And then the turbine is the energy output over the energy decrease of the fluid. So those are the inverse, and then it's the increase versus the decrease. So just remember those for the pump and the turbine. Okay, and so then we have the mechanical efficiency of a fan is the ratio of the rate of increase of the mechanical energy of air to the mechanical power input. And then it has a formula over here that's worked as well. And then we have additional formulas. We're going to use a lot of formulas, so I'm not spending too much time on them now because this is more of just a theoretical, just introducing you to the terminology and overall, but you will have, I find it's better to separate them out and actually give lectures on working the problems as well. So you have motor, which is output over input, generator, which is output over input, and it's electric or mechanical respective there. And then you've even got the efficiency of the pump motor, and then you've got the efficiency of the turbine generator. And then over here, you've got the overall efficiency of a turbine generator is the product of the efficiency of the turbine and the efficiency of the generator, and it represents the fraction of mechanical power of the fluid converted to the electrical power. And you see that little formula down here. That was a really wordy way of showing that, but we will also be working these. The conversion of energy from one form to another often affects the environment and the air we breathe in many ways, tons. And thus, the study of energy is not complete without considering its impact on the environment. And we just talked about this. Pollutants emitted during the combustion of fossil fuels are responsible for smog, acid rain, and global warming. The environmental pollution has reached such high levels that it became a serious threat to vegetation, wildlife, and human health. So here you see, and countries are implementing different things, but they are all implementing in way of reducing this. So energy conversion processes are often accompanied by environmental pollution. Motor vehicles are the largest source of air pollution. So there's a big push for public transportation to reduce because it's like, a single train that produces, X, Y, Z of all of these chemicals, but they can carry like 300 people, right? Versus needing 300 individual cars because the train is not putting out 300 times that amount, right? The difficulty in America, because I have lived overseas in a couple of different countries that do have really great forms of public transit, is that in the US, it's very spread out. So the likelihood that all 300 people need to go within walking distance of one stop is slim unless you are in those heavily populated areas like DC or New York or, San Diego, things like that. You can't just put a train out in the middle of Tennessee and hope all 3 people are going to go to the same place. So it's definitely in other countries that are much smaller, it's definitely easier to do in a setup, but they are making great headway to that, or to setting that up for it to be feasible. Smog, I'm not going to go into too much of this. You can pause and read it, but this is just going into what smog is, what the hydrocarbons are, what the ozone, of course the ozone, things like that, carbon dioxide, and dust and soot, things like that. It's basically all really terrible. And then here's the ground level ozone, which is the primary component of smog, which forms HC and NO react with the sunlight on hot, calm days. So it's just telling you how it works. And then acid rain is the sulfur in the fuel when it reacts with the oxygen to form sulfur dioxide, which is an air pollutant. So then it goes into there. And this is just a schematic of it as well. So you have these plants, and then it gets heated up by the sun, and then it comes and you've got acid rain. And then the greenhouse effect, which if you've all been in a car on a cold day, but the sun is baking your arm through the window, you have experienced the greenhouse effect. And it means glass allows the solar radiation to enter freely, but blocks the infrared radiation emitted by the interior surfaces. So this causes a rise in the interior temperature as a result of the thermal energy buildup in a space or a car. And then we've got carbon dioxide, water vapor, and trace amounts of some other gases such as methane, nitrogen oxide, acts as a blanket to warm a nice, wonderful earth blanket at night by blocking the heat radiation from the earth, and it results in global warming. And they're also called greenhouse gases. I'm sure you've heard of that. And it's produced from burning the fossil fuels. And then a 1995 report has shown that the earth has already warmed about 0.5 degrees Celsius in the last century, and they estimate that the earth's temperature will rise another 2 degrees Celsius by the end of 2100, and a rise of this magnitude can cause severe changes in weather patterns with storms, heavy rains, flooding, droughts, things like that. And so it may not seem like a lot, but we're in what's called the Goldilocks zone for the universe, and it is incredibly fragile. It is incredibly fragile in that if we just warm up 2 degrees Celsius, if the earth warms up 2 degrees Celsius, we're talking huge hurricanes, major floods, no more wetlands. Coastal areas are probably just deserts now. It's just, it's so fragile. So these changes are very different. And it's also important to know that we are relatively new to studying the Earth. The Earth is very old, and our records do not go back that far. So we are definitely going on hypothesizing based upon the most amount of information that we can get. And then here it just kind of goes into what is produced by cars, and then renewable energies such as wind are called green energy since they emit no pollutants or greenhouse gases. So there are ways to get energy without putting out no pollutants and no greenhouse gases. And then these are the summaries. We kind of went into it, energy and environment, things like that. But most importantly, we really I want you to know, the forms of energy, right? And then energy transferred by heat, energy transferred by work, right? So we've got heat and we've got work, and then mechanical forms of work, right? Because we've got different types. We've got like turbine work, we've got shaft work, we've got, all those things. And then you've got forms of energy, and you've got the different forms of heat transfer. You've got convection, you've got convention, you've got radiation, things like that. First law of thermodynamics, what is that? Energy is not created or destroyed, it's transferred or converted. And then energy conversion efficiencies. Of course, if we're going to be converting energy, we want to make it efficient. And then energy in the environment and how that interacts with us. Okay, so that was the end of chapter 2. And I will see you back for lecture, I believe it's number 5, in the start of chapter 3.